My name is Joe Grand. Let's see. I do computer stuff. I do electronic stuff. I designed a few years of DEF CON's electronic badges, 14 through 18. And today is a talk that I've been really wanting to do for a really long time, and that's look at different ways to get access to inner layers of circuit boards to help with reverse engineering. So we see a lot about, like chip hacking stuff that Chris Tarnowski does at a really microscopic chip level. And then we see a lot of stuff of kind of hardware hacking, embedded system, component level, connecting up through JTAG interfaces and through UART ports and all sorts of stuff, which is slightly higher level, but we never really look at the board level. And this is something I've wanted to do for a really long time, so I'm excited to give this presentation and lucky that I guess I convinced enough people at DEF CON to let me give it. Okay, so just to get started, reverse engineering PC boards, isn't really that much different than reverse engineering anything else, except we're looking at a circuit board. So we're basically undesigning a system that's already been built. In this case, for this work, I'm sort of assuming a black box type of scenario. Maybe we open up a product. Maybe we get access to some circuit board in the field that we want to figure out what's going on with it. So we take that system and we use destructive methods, we use non-destructive methods, whatever we need depending on the situation to get more information about the board so we can actually then go and perform an attack or do something else. And the main ways we would do this would be to access each individual copper layer, which is really the primary thing that I'm most excited about. Once you get those, if you get each layer of the board, sometimes you have a multi-layer board, and I'll describe the kind of typical board composition. You can kind of lay those out together and stack them and adjust opacity and do image processing types of things to actually trace out connections. And once you do that, then you can say, oh, okay, this part's connected to this part. Maybe microcontroller is connected to external memory. Let's go after the external memory. It's basically to give you an idea about what's going on. Oh yeah, also, so besides the obvious sort of things of like figuring out how the system works, also good to kind of verify security schemes of things. But what I really sort of like about this is injecting kind of new behavior into a device. And this is something that's like, yeah, of course you have the kind of standard research types of things or forensic analysis or whatever, but if you have the board design, you basically have the fingerprint of the board. And if you have that board level, then you have firmware and other things, you can kind of clone the thing. But injecting new behavior, lots of governments have been doing that for quite some time, and they must be using some of these techniques, I'm assuming. But it's sort of a, kind of an interesting area because now you can take a board, delayer it, figure out what's going on, and then find a good location where you can inject something that isn't going to be detected. So whether it's enabling some new feature, whether it's some surreptitious monitoring or whatever it is, doing it at a board level, people aren't really thinking about like, oh, what if somebody changed the board layout between the time I sent the board out to fab and the time it came back from China? Right? No one's really thinking about that. At a chip level they are, because there's lots of counterfeits and all sorts of kind of gray market areas for chips. But circuit boards, you don't think about the fact that, oh, what if somebody's adding functionality to a board? But you should. All right, so we're going to look at three different kind of sections. I've broken this out. The first thing is solder mask removal, basically just getting access to the top or bottom layers of the circuit board. Then we'll look at delayering for multi-layer boards to how can we figure out, how can we get access to each individual layer of the board. And then imaging, which is going to be non-destructive types of stuff. And a lot of the tools that we're looking at here, you'll see, are not that impressive, but it's just never really been talked about. So we have some manual methods, we have some automated methods, we have some chemicals, like all these different things. I thought it would just be cool to put them all in one spot. And a lot of the things that we're using also are kind of designed for, at least from the imaging side anyway, designed for failure analysis. So they're standard engineering tools that legitimate designers are using and legitimate fabricators are using that we're using for hacking hardware and for reverse engineering. And that's something we can do a lot, like take advantage of tools that are out there and use them to our advantage. This work was done for a cyber fast track project. So our tax dollars at work to let me play with circuit boards, which was awesome. I was going to do it anyway, but I didn't tell them that. So before we can actually start, getting access to the layers and start doing some of these techniques, we kind of need to understand how a circuit board is put together. How many of you guys are familiar with circuit boards and how they're built? About half. How many have designed a circuit board? That same half. Okay, cool. I guess that makes sense. Yeah, okay, so half of you guys are familiar with this, half aren't. That's pretty good. But circuit boards are basically a sandwich of layers. So you have your insulating layers and you have your copper layers. Your top layer is going to be copper, and then you have your insulating layer, and then another layer of copper and insulating. So I like to call it a circuit board sandwich. And I made a shirt just for this occasion. I don't know if you can see it from way in the back. Circuit board sandwich, yeah. And I don't know, because circuit boards are awesome. So this is, the circuit boards do two things. One of them is they provide this physical carrier. So you have all your components, they go on the board. It's this physical carrier where the components can actually connect on the board. And then they provide the electrical pathways. And if you figure out what those pathways are, that's how you can do your reverse engineering. Let's see, this picture on the right, this PCB cross-section, this is a 16-layer board that I just happened to pull out of my stack of circuit boards, and it's a cross-section. So we're looking at each individual layer from the side view, and there's, you know, a bunch of, I don't know, what is it, six, I don't know, I can't do the math in my head, but there's a bunch of thin layers, and then there's two thick layers in the middle, and then a bunch of other thin ones. So this is something, if you're reverse engineering a board and you do a cross-section, which is not uncommon, sometimes you can do it from the edge of the board just so you can see, try to get an idea of like interlayer spacing. The inner layers are thicker, which probably mean that's power or ground planes, you know, or something carrying some sort of high current there. The picture on the left is an awesome, awesome thing if you can ever get it. It's the Dutch-Indonesian spekkoek, which is an awesome layer cake. Not a PC board. And they taste much better than PC boards. I can guarantee that. But as soon as I saw this, I ordered this at a restaurant when I was in the Netherlands, and actually I didn't know what it actually was. And they brought it, and I was like, oh my God, this is awesome. I'm going to put it in my presentation. So now you know what circuit boards look like. There's a bunch of other layers on a board. So you have your copper and substrate layers, but you sort of have other stuff on top. So the silkscreen layer, usually white markings on the board, sometimes other colors. That's made of like a printable ink or epoxy. Usually part designators are on there. Sometimes you'll see manufacturing logos. Sometimes you'll see markings by engineers for test fixtures or test points, things that we can take advantage of. That's at the super top layer. The next layer down, the solder mask, which is the coating that makes the boards green or white or blue or whatever, basically is a protective layer that's going to protect any area of the copper that is not intended to be exposed. So if you look at your DEF CON badges, all those copper pads, those copper circles, are intentionally made to be exposed, so you can solder to them and tap onto them and do things. If you look carefully, you can see a bunch of traces underneath the actual solder mask, and those are things that are not intended for you to hack on. That doesn't mean you're not allowed to go there and do it. It just means the engineer doesn't want you to access those. And it protects the board from dust and corrosion and a bunch of other stuff. So we'll need to deal with getting through that solder mask layer. The circuit board fab now, kind of the capabilities of circuit board fab is almost approaching like high feature size chips. Like you're getting so these tiny fine features. So the state of the art stuff, like less than 1 mil, 1/1000th of an inch. Trace and space width. So you can have a copper trace of 1/1000th and then a space and then another trace. Just amazing, amazing kind of just density. Half a mil, less than half of a mil diameter laser drilled holes. So you're looking at circuit boards that are like highly, highly complex. The fabrication technologies are amazing. Things like via in pad. A via is something that connects different layers of a circuit board together. Normally, like in a traditional PC board fab, you'll have a mechanical drill hole going all the way through the board, even if it's only connecting, say, layers 2 and 6 of the board. It's still going to go all the way through because it's just an easier fabrication process. But when you have via in pad, or even buried via, you can't even find the vias sometimes. It's insane. So via in pad would be like you have say you have like a highly integrated ball grid array device where there's a matrix of solder balls underneath a part, which is typical for most devices these days. If that pad needs to connect to an inner layer, it doesn't have to go on the top layer out somewhere down to a via somewhere else. It can have a via straight in the pad and going straight down into an inner layer, and you would never see it unless you did, you know, some of the techniques that we're going to do. So very, very advanced capabilities, but normally we're looking at kind of traditional capabilities, 3/1000, 3 mil tracer space, 8 mil mechanically drilled holes, and then buried vias. And buried vias are traditional vias, except they only connect the layers that need to be connected. So you can't access them from the outside, which makes reverse engineering harder. But yeah, I mean, just amazing what PC board fab can do right now. This picture here is an iPhone 4 16 gig logic board, a cross section of that. 10 layer board, super thin. What is it? 0.75 millimeters or something. Let me convert that. 29.5 mils. So 30 thousandths of an inch thick. 10 layers. I didn't actually convert that in my head. I have it in my notes. I know someone was clapping. He's like, wow, he can do math really fast, but I can't. Thank you for joining us, you two fellows. Please sit down so I can continue, so you don't interrupt me anymore. I know them, it's okay. Yeah, so this type of board is super complex, and I used this iPhone board in a lot of the experiments. I wanted to use kind of traditional standard boards. I did some 2-layer boards. I made a custom 6-layer board that I had complete control over the design on each layer. I knew the layer spacing. I knew everything about it, so I could kind of validate the success of the of the various techniques. But then the iPhone board is a real world situation of a actual consumer product using current state-of-the-art technologies. So I grabbed a bunch of these things on eBay, just bare boards, and they were actually Apple iPhone knockoff boards. They looked great, except there was like very noticeable defects and cracks in them, and just really weird things. I just couldn't imagine someone actually buying an iPhone board on eBay and building it. But I don't know. Apparently, that's what people do. But it was fun, to use something like this to actually prove, like, okay, the technique is not just going to work for like a hobbyist board; it's going to work for the real deal. So I mentioned that we want to try to get access to the inner layers, or all the layers of the circuit board. And if you do that, if you can only access, say, the top and bottom layers, that's still better than nothing. But really, if you get all layers of the board, whether it's a 4-layer board or whatever, then you can start really putting together the entire design. So this thing here, I'll show you this again at the end of the presentation with one of our techniques. This is 4 layers of a speech synthesis board that I designed. That is a great reference because I know exactly what it's supposed to look like. If we also know the components, almost all of this stuff, except maybe some of the non-destructive methods, assume that there's no components on the board. So if you're going through your process, you would make note of the components, make note of part designators, and then take them off the board to actually start destructively getting down to the different layers. If you know the components and then you know the board layout, then you can recreate a whole schematic. And with that schematic, which is like an electronic roadmap for the entire system, then you totally win. All right, so the first set of things we're going to look at is solder mask removal. This is getting access to the top and the bottom layers, because those are the only 2 that are protected by the solder mask. Lots of different ways. You'll see, the mechanical way, or the manual abrasion and mechanical. But we'll go through a bunch of these and sort of see. It's surprising, like a lot of the stuff you'll see, the lowest tech ends up being actually the most useful, which is great for us because it's also the cheapest. So what I'm going to basically do is just run through a bunch of these techniques. And I should mention, so when I was doing the Cyber Fast Track work, there was a bunch of stuff that didn't work. And I don't have the time to go through all the stuff that didn't, so I have one slide for each section of stuff that didn't. So you don't have to actually go and fail the way I did. I tried lots of stuff. I'm also releasing, these slides are already on my website as of today. So if you go to grandideastudio.com or just search for whatever the title of this talk is, it will show up. I'm also having an academic paper that's going to be published at Usenix Woot next week or something. So that will be basically what I'm saying here, except written down in really nice sentences. That took a really long time to write. Okay, so sandpaper is sort of like, all right, everyone's like, oh, sandpaper. Everyone has sandpaper. It seems like a very obvious sort of solution, and it is. But it works great. So this is something, for this particular situation I had, the set of boards, put it down onto this work surface, and just sanded it. And it worked great. But the one thing you have to kind of worry about, though, is you have to make sure the sandpaper is actually, really kind of planar to the surface. You want to make sure that you're evenly sanding. Because if you're not, you're going to get wear, and you're going to end up sanding down into the substrate, or into the copper and then into the substrate, which I'll show you when we do some of the delayering stuff. So it's basically just using sandpaper. You can put boards of the same height on either side of the board you're sanding. That will keep things really level. But yeah, the effective, lowest cost way to do it. Here are just some results of that. Different grit sandpaper, depending on the surface finish. Some circuit boards have, say, a gold surface finish on the pads. Some have a solder mask or a solder over bare copper, where it's basically like solder kind of leveled or blown over the pads. So depending on the surface finish that's required for the board, you might need a different grit sandpaper. So the thicker the coating or the thicker the surface finish, you might need like a stronger sandpaper first, a lower grit, and then you move up to higher grits as you get down to start removing that solder mask. But you can see even like on the iPhone board, 400 grit sandpaper, you can wear off that solder mask and you're not wearing down that copper at all if you're gentle. Using a fiberglass scratch brush, which I hadn't known anything about before, but I guess they're used mostly for like scraping off rust on metal that you're working with, or cleaning off different types of parts, is great for removing solder mask. It's better for selective areas. So say you do want to access a single trace on a board or a single via on a board. That's what the fiberglass scratch brush is really great for. You can do a whole board with it. It will just take a little while. And make sure you wear gloves, because this stuff will flake off and you'll have tons of splinters all over your hands and fingers and everything. I think I posted a picture of some of those in my thumb at some point. And I think one person actually realized, like, oh yeah, fiberglass shards are really bad. Should have worn gloves. I'm like, I know. Thanks for that tip. So that's the scratch brush. Sandblasting. You don't normally associate sandblasting and circuit boards, right? Or at least I don't. You sort of associate it with, like, building motorcycles or something like that, using it with big pieces of metal. But it actually works pretty well to scrape off solder mask coatings. So I went to a place called Tech Shop, which is sort of like, I don't know, like a fitness center for nerds or something. They basically rent machine, they teach you how to use the machines, and they let you use the machines and everything. It's a really, really cool idea. And there's places all over the country, different types, other organizations do the same thing. But I went over there and said, hey, I'm working on a project. Can I use your machine? I'm not a member. I don't want to sign up for a month to use your machine for an hour. Could I please come in? And, stood around for a long time until finally they're like, fine, okay, come in. So I gave a guy $20 who was about to go on his lunch break to do this stuff for me. It's amazing what you can get when you ask nicely and hold money up. Yeah, so this one, we had to be really careful, because sandblasting normally is just a very kind of high PSI, high rate of speed type of application. So the operator tried to kind of scale it back a little bit and be a little gentle on the board. We had some pretty massive failures, but once he got the technique right, you just use a standard type of sandblasting machine. We were at a 60 grit aluminum oxide, 80 psi. And that's their standards. They didn't even modify that, but he had best success when he was like 6 to 8 inches away, shooting it at an angle. This works really well with kind of standard types of boards. We put an iPhone in it and the thing just got destroyed to shreds. It was just way too fragile. But standard types of boards, even 2-layer boards that have a really thick substrate, that seems to work best. But we got some noticeable pitting in the copper, so technically there's damage in that copper. But for our purposes, it doesn't really matter. As long as we can get a good image of that layer, we can then do post-processing and clean it up and everything if we want to. They do make things that are called micro abrasive blasting cabinets, which are much smaller for like fine detail on jewelry and things, and that probably would have been a better solution, but I didn't know where to get one of those. Yeah, okay. This is fun. This is my favorite part. Making meth. Oh wait, no, wrong conference. Removing solder mask. So these chemicals, there's lots of different chemicals out there, and if you search the internet, people are like, oh yeah, you got to use the sodium ethanol methylate to dip it in the thing and hold it under the heat lamp and the Bunsen burner. They say all this stuff, but I don't think people actually ever actually test that stuff, except the people that like blow their fingers off. So, I was a little wary of stuff I read on the internet, and I'm like, I think I'm going to use chemicals that are actually designed for this type of thing. And luckily, there were chemicals that exist. So there's 2 chemicals I looked at that were actually used by circuit board fabricators. If they mess up the application of solder mask, there's a chemical they can use to dip the board in, strip the solder mask off, and then they'll have their bare copper again, and they can redo the process. So it sort of makes sense. But this is one of the things, legitimate people need to use it. We can use it for reverse engineering process. So I don't think I really have to say how dangerous this stuff is, but it was really dangerous. So this is I don't have a fume hood or anything. I don't have like proper OSHA compliance or anything. This was in my backyard, and I went to Home Depot. So basically, like as part of the DARPA project, the first thing I got to do was go on a shopping spree. And one of the things was, Home Depot for supplies and like electronic surplus store for supplies. So I, basically got to go and have a shopping spree and buy all the stuff. So I have like a chemical mat, a mask, respirator. What is that thing? What are those things called? Those hot plates? Is that what they're called? Hot plates. No, it's not a stir plate. That has a magnet in it to stir it around or something. It's just a hot plate. Got it on eBay. And then the chemicals and rocks to hold the thing down. So this was in my backyard, and this particular house that I lived in was diagonal to a hotel, with all of the doors of the rooms facing down into my backyard. Which I'm sure they loved it when I was in the hot tub, but this I think freaked them out a little bit. When people are like, "Oh, I'm going to have a nice vacation in San Francisco," and then they look out and they're like, "What is this guy doing, like dressed in this crazy suit?" Which was And there actually was a black car outside of my house for 2 days when I was doing this work. I shit you not. And I was like, well, who cares? Like, if somebody comes and sees all this stuff, like, I'm doing work for the government. I have a piece of paper that tells me I'm allowed to do. They approved it. I'm allowed to do this. But nothing ever happened with it. But yeah, so I wore the suit, and it was actually really funny because with these chemicals, you have to heat them up to a certain temperature because that helps with chemical reactions and all this crazy math stuff. So I had this full chemical suit on, but who took the picture? It wasn't me. Yeah, so my wife took the picture, and some of you guys might remember her when she was pregnant and called my phone in front of 8,000 people or something at DEF CON a few years ago. She took the picture, and as the stuff was like heating up on the hot plate, and she got really pissed because apparently that stuff smells really bad. But I didn't know that because I'm wearing a respirator. So she took the picture, and she's like, wait a second, why are you wearing this stuff, and how come I'm not wearing it? And she got super, it was, I would swear if I'm not going to swear because I'm a nice person. But she was really angry and, kind of going off like a trucker. And so she ran out and shut the door and stuff so the smell wouldn't come into the house. But I guess it was really bad. And actually the fumes did go into the house. So next time, if I do this, I'll do it a little further away from the house. Or just buy her a respirator. So yeah, this was, that was fun. But I was really freaked out. I don't normally deal with chemicals that much, except when I used to etch circuit boards. And I would just dump all the chemicals down. Yeah, someone else etches circuit boards. But did you dump the chemicals down the drain? Oh yeah, it's Space Rogue. Yeah, he was there when I was etching circuit boards. So yeah, chemicals, I don't know. They're very effective, as you'll see, but also just really dangerous and freaky. So it turns out both of these chemicals that I use, there's 2 of them. One is a US company, one's a UK company. Neither of them will attack the actual substrate, which is good for solder mask removal, but it wouldn't work well if we're trying to delaminate the board. So we basically heat the liquid, put the circuit board in, rinse it, and just brush it, and the stuff comes right off. It's pretty cool. Like pretty much right when you put the circuit board into the heated chemical, it just starts kind of flaking off, which is really neat. And the time depends on the temperature and the thickness of the solder mask and things like that. But the result is super awesome. Full copper exposed, no abrasion on it or anything like that. Really, really well done. And then lasers. Lasers. Who here has a laser? Yeah. A lot of people, right? Like they're not an uncommon thing anymore, like a laser cutter or something in your hacker space. The one I use is just a really gigantic one, but it's no different than, I don't think, much different anyway, than the ones that you have in hacker spaces where you're doing laser engraving on your iPhones or something. So this one I went to a company in Milpitas called A Laser and said, hey, I'm wondering if we can use your laser and shoot it at circuit boards and see what happens. And they're like, yeah, that's a little weird, but okay, sure. So I went by, which is awesome. Places really, they're willing to do kind of interesting things, because for them, I was talking to the operator and he's like, yeah, this is totally fun because we had no idea what's going to happen, and it's way better than like way better than what we do day in and day out. So for them, it was something fun. And this happened almost every place I went. It was kind of fun for the operators because they didn't know what to expect. In this case, who knows? I was worried that we were going to like set the place on fire or something. Thank you for that. Okay, all these guys are wearing. I knew this was going to happen. I guess this is like a DEF CON tradition. Thank you guys. I love you guys so much for that. Thank you. I actually told them before the talk, I'm like, nothing's going to throw me off. Not even a giant dong. No, you said you weren't coming on stage. No, you broke the rule. Take your mustache down. Okay. All right, where were we? Okay, come on, get that out of here. Okay, so so the lasers that we're using here are basically for cutting material like flex circuits, like flexible circuit boards, for cover layers, for doing, say, like stencils or solder stencils for circuit boards. And we were just trying to see, like, could we shine a laser and would it get through solder mask? I actually went to also use them to see if we could actually get to inner layers, which I'll explain later on. That doesn't really work. But in this case, it did. Like, we just had a single pass of the laser at a medium power. I don't know what that means because he told me there was low, medium, and high. So I figured, I'm like, let's just start with medium and just see what happens. So we did one at medium power, and it worked. The more you do it at medium power, or if you had high power, the more energy you're shining at the board, eventually you're going to destroy the board. But in our case, just a single pass was fine. We removed the we removed the substrate. Very little damage to the copper or to the substrate underneath. So the one on the left is from my test board, my 6-layer test board, and then one on the right is from an actual iPhone board. This one was interesting because this connector that we've exposed is traditionally under solder mask. So if I'm looking at a board and I see something like that, a connector under solder mask or very obvious test points under solder mask, I would say, oh, okay, that's probably like a programming interface or some connector that's used during development or some test points that the engineer wanted during development that then they cover over with solder mask after. So we can kind of use that as a clue if we're reverse engineering and say, okay, let's get access to that. In this case, we did. It took about 30 minutes to set up the machine. About, I don't know, I can't remember the time, but it was very fast, maybe 30 seconds or a minute to do the passes to expose the solder mask. So if you wanted to do a full board for that, though, it would take quite a while to actually do that. And that's why it's like manual methods seem to kind of work better than some of the high-tech ones. Some of our failures, I tried to use a knife and a mechanical eraser to kind of rub the solder mask away. Dremel tool, a bunch of mechanical abrasion types of things. Other chemicals, not from the internet, but things that I talked to people about. And different types of heat. Because on the internet, someone's like, yeah, if you just use a heat gun and like heat the solder mask, it's gonna melt. But the thing with solder mask is it's actually, if it's properly designed, it's meant to sort of withstand a lot of heat. So it did its job. So these are sort of some of the failures. So the next set is delayering. This is where I think things get more interesting because now we're starting to look at the inner layers itself. So sandpaper, again, kind of a manual method. And then we have mechanical, bunch of different mechanical stuff. And this is where things, I started really learning a lot about the process, as you'll see. So again, sandpaper, very effective, low-cost method. I just took the board, double-sided taped it to the work surface. But as opposed to the solder mask, which if you're just using sandpaper on solder mask, it's going to come off pretty fast, a few minutes maybe. When you're trying to actually delayer an entire layer of substrate that could possibly be 40, 50, 60 thousandths thick, it's going to take a toll. I don't care how strong you are, it's going to hurt. And you're going to get really sweaty, which I know a lot of people don't like. So what you can do, instead of just using sandpaper, handheld sandpaper, you can use like a sanding tool. So on the left, I have a sanding stone, which is like a 60 or 80 grit stone, so you just get a better grip on it. Or I have a Norton sheet sander tool, which you attach the sandpaper to this thing, and then you have a handle, and you can actually go back and forth. But it takes a while. So here's a little video of it. Time lapse, of course. So I'm taking the stone, trying to get the top copper layer off, and then we'll have the substrate, and then I got to work on the next layer. So first the sanding stone, try to use that, sort of works. Then I have the sheet sander tool, and little by little it's coming off. But just like with the solder mask removal, you kind of have to be careful about the edges of the board, because if you're not sanding straight back and forth, you're going to have this wear along the edges, and I'll show you the result. So there it is. It looked like it happened really fast. That was 20 minutes, and I was drenched at the end. But here's the result. We had a little bit of scratching of the inner layer, and a little bit of wear around the edge, but we have basically the second layer of that 4-layer board. So pretty cool, I think. So I had the second layer exposed. Now I was like, all right, we have to expose layer 3. Let's try to use a Dremel tool. I'm not that good with mechanical things, like tools or anything else that has moving parts. So I had a lot of failures with the Dremel tool. A lot of problems. Didn't lose any limbs, but damaged a lot of stuff along the way. But it did turn out that this one type of tool, this flap wheel, 120 grit, 3/8 inch wide flap wheel, actually worked pretty well. If you kind of go back and forth across the board, you're going to get through that substrate a lot faster than you would manually, using a sheet sanding tool. I don't have a video of it because you guys know what a Dremel tool looks like when it works. But here's the result. This is layer 3. Yeah, I heard someone laughing. There's something wrong with this picture, isn't there? There's like a whole corner of the circuit board missing. Yeah, so I mentioned, right? I'm not very good with mechanical things. With practice, this would obviously be a better thing. But it works fine. It's just really hard to control the Dremel tool. I mean, you have a thin kind of, moving wheel. It's just really hard to control. But when I did that, I was like, well, wait a second. I'm just doing this mechanical abrasion. Why don't I use my CNC milling machine to try to automate that process? Oh, that took me 9 minutes, by the way, with the Dremel tool. So CNC milling machine, I just happen to have one in my office next door to make circuit boards, because circuit boards are awesome, and you need to make them all the time, I think. So this is a T-Tech Quick Circuit 5000, and it's basically just a really accurate CNC. And I used actually a special end mill from this company called Think and Tinker, which was designed as a carbide end mill specifically for cutting kind of fiberglass types of material. So there's the setup. Have my computer running the whole show, and then the milling machine itself. So what I did a few different experiments. First, I started with the known reference board, my 6-layer board, because I knew how much I could increment each layer before I would get access to the next layer of copper. I knew the thickness. So I basically just used the machine and kind of manually controlled the machine, adjusted the Z-axis for the depth to come down, and just kind of moved the milling machine back and forth. This particular board, you can't really see the left image at all, or the right one really. But the left one has a bunch of numbers for the different layers. So layers 1 through 6 are all numbered. So what I did is just went down and for each layer exposed those numbers. So I could prove, okay, now I can access layers 1 through 6. That was no problem. But that was sort of a board with very thick interlayer spacing. So it was sort of like cheating. So I decided to do it with the iPhone. And in this case, I didn't want to manually control it because I wanted to have a precise outline that I was working in. So I created that inside the tool and adjusted the Z-axis in 1 mil increments. So I'd basically run the rub out of this particular rectangle, adjust the axis, run it again, and keep running it until You guys are so funny. You're dirty. So I'd keep doing the operation until I could almost see the copper, and then I would use a fiberglass scratch brush to do that really fine removal of the substrate. So here's a little video of just doing like a little bit. I don't know how long this video lasts, but it's like taking off just a super thin layer of that substrate. I did that for a few hours until I got it right. But it actually worked. So I could see inner layers of that 10-layer iPhone board, which is seriously complex. But if you do that across multiple sections, you can reverse engineer the entire board. And if you can do it on something this complicated with that technique, you can pretty much do it on any board out there, I'd say. So last one of delayering is surface grinding. This was another one where I was like, okay, I'm doing the Dremel tool. It's like, how else can I do it? What other techniques? Surface grinders are these amazing machines that are used to grind down surfaces, to create nice surface finishes, and to do all sorts of crazy metal work. We have this rotating wheel on a rotary table, and the table moves around, and the wheel stays where it is, and it's just a very, very, very cool thing, but gigantic. So on the left is a typical surface grinding machine. Went to a place in Oakland, and this is like a straight up metal shop. I don't think they deal with computer, tech people very often. So I call them up, I'm like, hey, I want to grind down some circuit boards. And they're like, yeah, I don't know about that. And I was begging because I'd heard that surface grinding would be awesome. And the one guy I know in San Francisco that had a surface grinder didn't want to do it. So he's like, try these guys, try general grinding. And eventually they came through, and it was amazing. So we did it like after hours, like 8 p.m. in like the worst neighborhood in Oakland, where they escorted me to my car after the work was done, which was awesome. Because I guess I can't defend myself, at least in that neighborhood. So what we did is we had this metal block, and the surface grinders have a magnetic chuck. So you mount whatever you're working with. Usually it's metal, so it just goes directly on this magnetic chuck, and then you can work with it. But the circuit board is non-ferrous, so we had to put it down onto a block, and then that would hold it into place. And we basically, this thing had depth control of 0.1 mil increments. So my machine was 1 mil, give or take. I think maybe it was half a mil, 0.1 mil. So even a machine like that size is way more accurate. Here's the process. Does a little dressing of the wheel, and just comes down and just grinds the board. And does this whole process. It takes like it's like a 45-second process or so. And it doesn't really look like it's doing much, but it's actually shaving a really thin layer of the board. And we did this over and over again as we got down. And what you can do is, if you already know the interlayer board thickness, if you do a cross section first, or you look at the side with a magnifying glass, then you can just set that in the machine, and it will just automatically do it to that point where you need it. What we found is that the surface finish that was created by doing this was so smooth that you didn't have to actually get to the layer itself. You could just, as long as you could see it through the substrate, like it would polish the substrate so much that you could just see the layer through it. So these are the 4 inner layers of that 6-layer board. Pretty cool. And then a bunch of failures, heat, and laser doesn't work in this case for delayering, because laser energy affects materials differently. So if you're trying to cut through a layer of substrate, that's going to work differently than trying to cut through a layer of copper. And if you don't know how the substrate and copper are laid out on the board, you're just going to have a big mess. So for imaging here, we have X-ray, 2D and 3D. Pretty much everybody here probably has had an X-ray or knows somebody that does. But you probably don't know where to get access to an X-ray on your own. But it turns out that they're used a lot for failure analysis of circuit boards and of components on circuit boards. So they're used during circuit board assembly to make sure components are soldered on properly. So you can actually go to a contract manufacturer and say, hey, can I use your X-ray machine? And they'll say, sure. So that's what I did. So X-rays, shining through an emitter, and then the object is absorbing radiation, and then we'll be able to see the result. So we only see a composite image, not individual layers in this case. Here's what the machine looks like. Here's a Verifone pin pad from a pin pad device that had this active circuit board shield on top of some of the circuitry. So the X-ray, the 2D X-ray isn't really that great for complex boards because you get this composite, right? You don't know which layer things are on. But we can use it to get a general sense of what's going on. So in this case, this active shield had like 4 layers of basically a maze of copper that we'd have to figure out how to defeat that to get access underneath. If you have a really simple board, you can manually adjust the field of view and the angle of the X-ray to trace things out, but it gets really hard. Here are just some other kind of pictures of, there's that 4-layer speech synthesis board. So it's all right for certain things. But this is the real money shot right here, X-ray. This is the best, this blew my mind. This is the best part of the whole research. You know, CAT scans, where you go in that machine, spins around, and you get slices of your body parts or whatever. You can do that with circuit boards too. And just like there's contract manufacturers that have the normal X-ray machine, some of them have the 3D X-ray machine. And you're basically taking a number of 2D images at different angles around the object and then mathematically processing that down into slices. And here's like a BGA part, a ball grid array solder ball with a defect in it. Normally, these companies are looking at very, very small objects for very, very small defects. So I went in, actually called this company, which was recommended by Sonic Manufacturing, who did the 2D X-ray, and I called the CEO, and it turns out he was in Germany for a conference. And so it was like, you know, 5 p.m. my time and 3 a.m. his time or something like that. And as soon as I heard the ringtone change from the US to, you know, the European, I was like, oh crap. But he answered the phone at 3 in the morning. You know, I woke him up, which is not a good way to start a relationship. But he was just more than willing to help. And he's like, sure, I get back tomorrow, you know, let's set a date and let's do this. I've never done it. Let's try it. So it was totally awesome. And just a big surprise for everybody there. So what we did is we took 360 different images of that speech synthesis board, that 4-layer board. And then once we got all of that data, we loaded it into a manipulation program for 3D manipulation, moved through each layer, and we could like manually, you know, it creates a bunch of JPEGs basically, so we could hit a key and look through each layer. In some, you know, I don't remember the actual layer, the slice thickness, but it was just totally amazing. And the results will, you know, vary based on how many layers you have, the inner layer thickness, the weight of the copper, what other materials are used, because some high-end boards use very complex materials. But here's sort of here's the result of this CAT scan on our board. So we're slowly going through each layer. Layer 1's about to come up. Let's see. There it is. There's layer 1, and then layer 2 comes up. There's layer 2. Then we go through the middle of the board, the middle substrate, which is thicker than the others. Then layer 3 comes up fast. There's 3, and there's 4. So now non-destructively, we can see through the entire circuit board without having to do anything, which is awesome. Here's another view of it. So you'll notice thanks. It wasn't my machine, but thanks anyway. So you notice the field of view is small, so if you're going to do this across a larger board, you'd have to do this multiple times. It took about half an hour to get this done, so not unreasonable, but just totally awesome. We had some failures doing some acoustic microscopy that just didn't work at all. So in the paper that will be released next week, and in the presentation, I kind of broke this down into a characterization. So depending on how much time you have, how much money you have, likelihood of success, like how much you want to risk your life, you can look at the techniques and figure out which is good for which of your situations. I like the manual methods because it's just like a quick and dirty thing. But the X-ray was totally awesome too. All right, so next steps. There are some other methods that people told me about for delayering using a methyl ketone to actually strip the adhesive, interlayer adhesive, drum sander, which is sort of like a surface grinder, some other stuff I want to do. But really what I really want to do and what I've started to work on is a tool to take all of the layer images that I've now gotten through these various techniques and start a process to kind of automatically or assist in reverse engineering those back into something meaningful. So take those layers, do some image processing, figure out connections, and then possibly turn that into schematic. So maybe by next year I'll have something to show on that. It's a great opportunity for me because it's a lot of software, and I'm not much of a software guy, so I'll have to learn Python and stuff. So it's going to be pretty cool. So sort of like DGate, which is a tool for pattern recognition of silicon, and then ROMPAR, which is what major malfunctions tool to basically do pattern recognition as well. So this is, those are chip level. I want to do something board level and super cool. So there's the link with all the materials, but just go to my website and you'll find it. And there we go, the end. So thanks for coming. So I do want to mention, now that the camera's off, right? Okay. He's like, yeah, fine. So I do want to mention, this is a picture of my friend's leg with a gigantic tattoo of the JTagulator logo. And for those who were here last year, it was a hardware hacking tool I designed and released at DEF CON and Black Hat last year. And my name on his leg, which is also really weird. And a gigantic eagle coming down, drawn by Eddie Mize, the guy who draws all the art and sells art and donates all of his money and all of his time to the EFF to do this. So we thought it would be, well, this guy's, whose leg it is, thought it would be really fun to get a tattoo and then, you know, try to raise some money for EFF. So if you like Eddie Mize's work, which I think they already took it down in the contest area, but if you like his work, you know, donate to the EFF, or if you want to do something crazy like this next year, you get your own tattoo and let us know, and then we'll donate lots of money to the EFF. So, I don't know, totally insane, but I guess that's what happens at DEF CON. All right, thanks.